Hello everyone. In this video, I'm gonna work through the R script that will show you how to deal with probability distributions. R makes it very easy to work with it. For every distribution, R provides functions to generate random samples using the R prefix, calculate probability densities or masses using the D prefix, compute cumulative probability using the P prefix, and find quantiles using the Q prefix. This is the general template. So let's begin by clearing out the environment. We need the ggplot2 package for the visualization. So first we will calculate expected returns for a stock that has the returns -5%, 0%, and 10%, with corresponding probabilities 0.2, 0.5, and 0.3. So I create vectors storing these information separately and then calculate the expected return. So the expected return of stock A is 2%, which is consistent with what we find in theory. We can also calculate the variance of the return, which is var x, using this expression E of x minus E of x whole square. So the variance is 0.0031%. We can also calculate the standard deviation, which is a measure of risk, which is the square root of the variance. So this is the simple expectation operator. We can also look at the linearity property using that portfolio expected return. So I have stock A with a return of 8%, stock B with a return of 4%. Stock A is 60% of my portfolio, stock B is 40%. So if I run all these lines together, my portfolio's expected return is 6.4%. Pretty straightforward. Then we will move on to the binomial distribution. So I have total of 10 companies, which is my N. The probability of success, which here is defined as beating expectation, that is 60%. And I want to generate the probability distribution for all values of K. So if K is 0, that means no company is beating the market. And if K is 10, then that means all companies are beating the market. So I define N, I define P. My K values is is the whole range from 0 to 10. And then my binomial probability are the densities, which is the function d binom. That takes the arguments, the value of k's, the size, which is equal to n, and the probability, which is the probability of success. And then I'm going to create a data frame, and then for ease of exposition, I'm going to plot the binomial PFF. So that's that is what lines 55 to 75 or 74 is going to do. So I run this block of code and this is what I see. So these are the PMFs. So for every possible number of success, this is the probability of that event occurring. If I want to calculate specific probability, then I need to plug in that particular number against all the other information. So lines 77 to 79. So the probability of exactly 7 out of 10 companies beating expectations is 0.215, which is 21.5%. Probability that at least 6 companies beat expectations is probability P x greater than equal to 6. Now there are two ways of doing it. One, I can calculate 6, 7, 8, 9, and 10, or I can calculate. So what is P binom? P binom is the cumulative probability. So if I calculate the CDF of up to 5 and then 1 minus, I take that probability out, then what I'm left with is the probability of 6 and greater. So that's the approach I'm going to take over here. So the probability that at least 6 companies beat expectations is 63.3%. Let's spend a little time on what this means. So let's look at the documentation. So what lower dot tail does is that it takes a logical entry. The default is true. If I take that, if I set it as true, then I'm getting probability x greater than equal to x. If I set it as false, then I'm getting probability of x greater than x. So instead of doing this, I could have done something like p at least 5, and then take no, sorry, my bad. It shouldn't be true. So there are two ways I could have done this. Both ways are equivalent. Either is separately calculate up to 5 and then do 1 minus x up to 5, or I can set the lower dot tail equals false, and that gives me the CDF directly. Then is the discrete uniform distribution. I'm looking at a 6-sided die representing market scenarios. I define the outcome. I specify that each outcome is equally likely using the rep function. So my expected value is 3.5, which is consistent with theory. I want to calculate the variance using that expression. I use these lines of code, and that gives me the variance of the discrete uniform is 2.917 approximately. For Poisson distribution, I'm looking at the bank examples, loan defaulting. So the bank on average faces 3 defaults a month, so the lambda is 3. What is the probability that the bank will witness any default between 0 and 10? So I specify the parameter, I define the range of defaults 0 up to 10, and then I get the densities for all these values of k, and then I convert it into a data frame and then plot it. And this is what it looks like. And you will see that this is consistent with the table that is there in the slides. If I want to calculate specific probabilities, I plug in that number. So the probability of exactly 2 default loads is 0.224. So this value over here is 0.224. Moving on to continuous distribution, we start with the continuous uniform distribution where the value, the PDF is constant. I define the lower and the upper bounds, and I generate and I calculate the PDF. So for all values, the PMF for all values below 90 is 0. For all values outside of 110 is 0 again, because there is no density below 90 and above 110. And for all values between 90 and 110, the density is fixed at 1 by 20, which is 0.05. If I want to calculate the for a specific range, I can do that manually. That's probably the easiest way of doing it because it's just a constant and it's going to be 0.5. I can calculate the mean and the variance. Expected stock price, which is the mean, is 100, which is the average of 90 and 110. The variance of the stock price is 33.33, which is B minus A, 910 minus 90 squared divided by 12, which is 33.33. So the codes match the theory. For exponential distribution, we have to define the parameter. I define it as 1 by 5. And then I have a sequence of x values ranging from 0 to 20 with an increment of 0.1. And then I have the PDF, which I will represent using a plot. And as you can see, the PDF exponent decreases in time. So if I want to calculate the probability that order arrives within 10 seconds, so basically I'm calculating probability of x less than equal to 10, and I use a px. The p prefix stands for CDF, exp stands for exponential. So I define the function, plug in the threshold, and specify the parameter, and I get the density or cumulative density. So the area under the curve up to this value 10 is 0.865. So there is an 86.5% chance that the order will arrive within 10 seconds. And you can calculate 1 by lambda, which is the mean. Mean dot x is 5. Yes, 1 by 5. So that's 5. I can also calculate the variance, which is 1 by lambda square, var underscore exp. So this is 5 squared, which is 25. So this is again the memoryless property, means that if you've already waited for s number of seconds, the probability of waiting another t seconds is the same as probability of waiting t seconds from the beginning. So in other words, if no order has arrived for 5 seconds already, the probability of waiting 3 more seconds is the same as the probability of waiting 3 seconds from the start. So we can verify that actually using this line of code. And I'm going to do that by doing it in 2 different ways and looking at the variance. And as you can see, in both cases, either using the conditional probability approach or the memoryless approach, the number is the same, which means that the difference is approximately 0. It's never exactly equal to 0 because we are rounding off, but it is as good as 0. Then is the normal distribution. I define mu, I define sigma, and then I define a sequence of x values, which is starting from negative 0.15 to 17 by an increment of 0.001, which means that I'm looking at a return range from negative 15% to 17%. And then I'm going to calculate the PDF and then plot it for convenience. And I'm also going to add the vertical lines for the mean, plus, minus, 1, 2, and 3 standard deviations. So the red line over here, the red line is the mean. The blue, these two lines are plus, minus, 1 standard deviation, which represents 68%. The green lines over here represents the 95%. All areas within this bound covers 95% of all possible values. And the violet lines at the very end, all values between them are covered, they account for 99.7%. So very little values of this random variable lies outside of the plus minus 3 sigma range. We can calculate the probability of positive return using the p-norm function. So all values from 0 onwards will be counted, and that is 0.579. So there is a 57.9% chance that you will get a positive return given the variable follows this distribution. The probability that the return lies between -5 and 7% is 77%. So -5 over here, 7 is somewhere over here. This probability accounts for 0.77. To look at the central limit theorem, I'm going to start by setting the seed for reproducibility. I'm going to fix the number of days, which here is 21, and I'm going to do 1,000 simulations of that. And then I'm going to plot the histogram of the daily versus monthly returns and look at what we get. So this is what we get. So for the daily return, it's a little more granular. For the monthly returns, it's a little more jargon in that sense. And this is the course from the last slide. So you have a binomial with 10 companies, 60% chance of beating earnings. This is the code. Then we have the Poisson with 3 loan defaults per month. So this is the simulated binomial distribution of number of companies beating earnings. This is the histogram showing the simulated Poisson distribution with number of defaults per month. And then you have the stock return between 1% and S to 5%. The red line over here represents. So this is the R codes for this topic. I hope this was useful. If you have any questions, please let me know. I'll be happy to talk more about this. Thanks.